Okay, everyone. Good afternoon and a very warm welcome to this afternoon's webinar. It's my very great pleasure to introduce Giacomo Capodaglio and Bob Robey, both visiting us for this webinar from AMD. And they're going to talk to us this afternoon about porting and running applications on AMD GPUs, of which we are very pleased to have some as part of the ARCHER2 system.
So I'm Bob Robey. I'm the AMD Global Training Lead for the Data Center GPUs for high performance computing. And I'm in Los Alamos, New Mexico. I worked for Los Alamos National Laboratory for 24 years and joined AMD a couple of years ago specifically to help with documentation and training. And Giacomo, my great colleague, go ahead and do your introduction.
Thank you, Bob. Hi, everybody. Good to be here today. My name is Giacomo Capodaglio, and I work with Bob. I'm part of the training team for AMD for data center GPUs. And my background is in applied math and engineering. And before AMD, I also was at Los Alamos National Laboratory, and I just recently moved to Austin, Texas.
Okay, so we're going to go ahead and start into the presentation on AMD GPUs. And just to start out, we do like to create a positive environment for these sessions. So we're trying to build our community of application developers and experts in high performance computing. So we do want to appreciate all the people that are participating, no matter what level you are on your journey into this field. So let's try to stay positive, give time to other people in the session, and help others with insights into technical topics, and please respect everybody in our presentation and our discussions. So today we have laid out, we're going to try to cover a good overview of AMD products and how to program them. It's difficult to cover all of that in even the 90 minutes we have scheduled, and we do want to have some discussion. I always love to hear what people are doing with the applications they're working on, or what their interests, their scientific interests are. It's one of the great things about this community is we have a wide variety of different types of applications and interests. And so Giacomo and I will be switching off here to present different parts of the session. But this isn't just a product of Giacomo and I. Giacomo did most of the work putting this presentation together, but we build off of the contributions of a great team of people at AMD that contribute over time, and we draw from those previous presentations and work. So I'm going to launch into the AMD architecture and the memory model for the AMD GPUs. GPUs are, at least initially, quite a bit different than CPUs. So understanding their structure, their architecture is an important step into the programming GPUs. So what AMD has is one of the industry-leading GPUs. It today is in some of the leading systems across the globe, including the Lumi system in Finland, which is the largest system right now in Europe. We also have Frontier in the US, and Pawsey in Australia. And I'll go over a little bit why AMD has such a attractive hardware for application development. The first thing is that we are the only true APU, and I'm going to define an APU because, like everything else in computing, the nomenclature is sometimes difficult to follow, and the definitions aren't always easy to find. An APU is a marketing term, so it's especially hard to understand what we mean by APU. AMD is committed to some important policies. We're open source as much as we can be for the software for our GPUs. We do allow people to see the source of most of the code, and we've had contributions from some sites when they find a bug or an optimization that can be done to our code. And that's important because there's a lot of code involved in the software layer in GPUs. We do not believe in vendor lock-in. We're application developers ourselves, and we know you just can't afford to port to every vendor, every piece of hardware individually. So you will see that portability is a key part of the systems that we have developed. Our CPUs are really industry-leading products, and combined with our GPUs, they are a compelling product for application development. Right now, we have the leading floating point 64 performance. We are committed to HPC. I know there's a lot of talk about AI right now, and a lot of people chasing that market, but we're still committed to this double precision floating point performance. And you don't have to do anything special to get the floating point 64. It's an IEEE 754 standard double precision floating point. And so even for your applications, you'll be getting that kind of precision and performance. We also have a lot of support for machine learning AI, and most of the major libraries we have drop-in support that you can bring your application onto the AMD hardware and run it with usually no changes at all. So that's an overview of what we bring to the table for AMD products. And I'm going to first define an APU. So APU stands for Accelerated Processing Unit. It's AMD bought out ATI a decade ago, and with the goal of putting the GPU on the same silicon as the CPU. And at the time, the standard term was integrated GPU. To differentiate the powerful GPU that AMD was adding to the CPU, they coined the term GPU. And we're going to use that terminology still to differentiate, the kind of architecture that we have. So in this sort of diagram, the major GPU architectures today are in the bottom half of this this diagram, and for the most part, we've been running on discrete GPUs. The CPUs that AMD has have GPUs embedded in them, but they've been limited in their compute capability just because of the size of the silicon, and we'll show a diagram of that in a minute. But generally, applications have worked with this discrete GPU where you offload your calculations to this big card that is off the memory or off the PCI bus on the system. So we've mostly worked on discrete GPUs. This accelerated processing unit where it's combined with the CPU has been attractive, but it's never been something we could run on it. And I'll explain why it all of a sudden is far more interesting for those of us developing applications. I do want to mention that, you know, in our current hardware, memory really dominates the architecture today. And in the APU, we're dealing with a single memory space. So we don't have to worry about where the memory is, and both of the compute units use the same memory. In the discrete GPU, we have separate memory for each of the devices. And there's a few variants of this. You know, that's one thing that's really interesting in our high performance computing community, is that we come up with different architectures all the time, or variations of the current architecture. And so this is what the current breakthrough is in high performance computing, is this breakthrough in that compute capability of an APU. So traditionally, the problem with an APU was you just didn't have enough silicon to work with. You have this little chip on the motherboard, and you just don't have enough silicon space to add more and more compute. The breakthrough now, if we want to dump more compute capability into this system, is this chiplet design. And this sort of gets around the yield issue. As you grow the size of a chip, you know, the yield rate goes down on the production of the chips. And so by going to this chiplet design, where you place multiple small chiplets on a interposer layer, allows you to keep your yields high and put more compute on a device. And in this diagram, this is a hypothetical diagram. You can have different kinds of compute on that interposer, and even I/O and other things that are important to the computing capability. Here we're just showing the compute units, and so you can mix GPUs and CPUs, and by doing that you can create a new product quite quickly without having to redesign the whole the chip as a whole. So with that breakthrough, all of a sudden the APUs become quite interesting. The first product in this series just put all GPUs on that interposer, and that's in our MI200 series. And so we just were able to pack a lot more compute onto that device. MI300A, which just came out in the last year, that's a true APU. And if you look at this diagram closely, you'll see in the lower right corner, it looks a little different. That's because that's 3 CPU cores, or 3 CPU devices that are added in that quadrant. The other 3 quadrants are GPUs, and they're all addressing the same memory. The memory is this sort of band on the outer part of that chip, and all of the compute devices access the same memory. And that memory is high bandwidth memory, the industry leading memory product today. And so this gives you a really strong compute capability for applications. You can switch between the addressing the memory from the CPU and the GPU with one loop working from the GPU and the next loop working from the CPU. The 300X, if we really want to put even more compute on that device, we put all GPU units on it. This is really good for extreme compute workloads with high matrix multiplication demand. And so that's very attractive for AI work or math solvers that have very high arithmetic intensity. So this is the current lineup that we have from AMD, and there's different products for different types of applications. But I do want to stress, even if your application doesn't perfectly match this device, and this will happen at most of our centers where we have mixed workloads, these will all perform quite well even across a mix of application types. And then I want to define the memory model. So a memory model is really, the idea of a memory model is really crucial in high performance computing, especially with shared memory programming. And that is the key to the APU programming model, is that we need to guarantee when your data gets stored and is available to another thread, another compute unit. And this is to avoid race conditions. And that's, AMD has a decade of experience with synchronization and between compute units, the GPUs and the CPUs from the CPU chips. And so they've brought that across to these high performance computing offerings. So the 200s, MI200 series were the first product that AMD produced with this idea. And it is the product that is in most of the top systems for AMD currently today. So the Lumi system, the Frontier system, Satonics at Pawsey in Australia all use the MI200 series. And it's a powerful compute capability. And in this device, we have the memory coherent architecture that we have is based on a feature of the operating system, which will automatically move pages when you access them from one of the other compute devices. So if you access memory from the GPU that resides on the CPU, it will automatically move it for you from the CPU to the GPU. This is a great convenience for programming, greatly accelerates writing code. In the end, you may want to manage the memory movement yourself to improve the performance somewhat because you're in control of it. But this managed memory is really a key for making GPU programming a lot easier. You don't have to worry about where your memory is. So to implement that, you set an environment variable. It has this strange name, XNAC. That's comes from the implementation in the Linux operating system. So it's kind of a strange term, but it basically means that it's going to intercept a page fault and move the memory for you. So this heterogeneous memory management, sometimes called HMM for short, is a feature of the Linux kernel. So it's available on architectures across the industry, including AMD and other GPU vendors. So it allows you to intercept that page fault, do this page migration, and you know, there's a lot of key details behind it, but for the most part, the application developer doesn't have to worry about where the memory is for their application. So XNAC is the term from the Linux kernel, and so it's going to, when a memory fault happens, it's going to move the memory for you. You can control this by setting the HSA XNAC. HSA is the lower level programming language on the AMD GPUs. So this is basically setting an environment variable to say to turn this feature on. It can be set at boot time. It can be set in your environment. It can be set when you do your compilation of your program. There are a couple of different settings for this flag. You can have where it's turned on, it's turned off, or it allows any of the models to be implemented at the next level in your environment. So you can compile it to force it to happen, or you can allow it to be specified by the user's environment with this environment variable. So you have a lot of flexibility on how you handle the memory. And so with our 200 series of CDNA2, when you access memory from the GPU, it's going to move it from the CPU to the GPU. With the 300 series, and specifically with the 300A, standing for APU, you have just one memory space. So you don't need a second memory copy or a second copy of the memory. There's only one copy on the system, and that makes much better use of the memory. You don't have to worry about who owns the latest version of the array, and you can switch between who is operating on the data. You can have small loops run on the CPU, larger loops on the GPU. So you have a lot of flexibility on the system. Since this is a new programming model, it has, you know, applications are still being adapted to really take advantage of this architecture. Now you can write your application so it can run on both types of GPUs, but there are some things you could do to make the APU model much more efficient. Okay, so let's just show what this means to the programmer. So, you know, to the programmer, when they're writing their normal CPU code, they have, this is sort of an example, very simplified example of CPU code where you allocate the memory. So you're allocating an array to pass in, an array to come out. You're going to operate on it, and then you're going to call a function that's written for the CPU. And then you continue working on the CPU. When you do this on the GPU, in this what we call an offload model, where you're offloading the work to the GPU, you have to allocate two arrays on the GPU for the data that is on the CPU. And then you have to copy the memory to the GPU, do the GPU function, synchronize, copy it out, and then you can continue operating on the CPU on the data. So every time we convert a loop or a part of a code to work on the GPU, we have to do all this memory management. That has been, this is what we call explicit memory management, and that has been the majority of the work for most programmers in porting to GPUs. And generally during the porting process, every time you move to the next loop, you have to think through, well, what memory do I have to copy over there? Who has the most recent version of the data? Is there some different path through the code that's going to have the wrong version of the data? And so this memory movement is by far the biggest part of the difficulty during the porting process. So when we have APU code, we no longer have to worry about the memory movement. And so this is applying to a true APU where there is only one memory space. Here we no longer need the additional memory allocations for the GPU. We still have that GPU function we've converted, and in different programming models, there's different ways of doing that conversion. And then we may need a synchronization call after that GPU function, and then we continue on. And so you can see that this code looks a lot more like the CPU code. It really does greatly simplify the porting process to the GPU. Now, I said this is on a true APU, but we can mimic this APU programming model through the managed memory as well. And so you can develop your application, let the system do the operating system and the lower levels of the GPU software move the memory for you. And so we get an APU-like programming model using managed memory. Now it will have memory movement that you have to do. So you will see the performance impact of the memory being moved, but it's much easier to do the programming. And it's compatible across all the GPU architectures and models that we've discussed. It also works on other vendor devices as well, although they will have to do that memory copy. So let's look at the performance implications here. So we saw that GPU code, the GPU code on the left when we run on the 200 series. It's going to move that memory from the CPU to the GPU. That memory movement cost, the hosted device copy, so the host being the CPU, the device being the GPU, is on order of 10 gigabytes per second. You can have two versions of your memory array on the APU as well if you still hold on to that two versions of the memory, or you can have just a single version of the memory. But in both cases, that memory copy time is orders of magnitude higher. And so we see, the GPU can access that single memory space at the order of terabytes per second. And that's why, this APU programming model has us so excited for application development. It just greatly simplifies the programming task. Okay, so here we're showing that simplified code for the APU, and you still can make that work on the discrete GPU, the 200 series and the 300X, but you will have that memory movement between the CPU and the GPU. In this case, on the APU, there's nothing that needs to be moved, and so your costs drop to essentially zero. Okay, so software porting process. This is, for many application developers, this is the most critical phase. How do I take my program and make it work on GPUs? And there's a lot of work that's required in this process, and part of it is that you want to get the same answer on the CPU and the GPU. So let's look at what this process involves. So we talk about this as being the 3 Ps, portability, performance, and productivity. And early on, the Department of Energy and the greater HPC community realized that this was the critical issue for exascale computing. You know, you really needed, you could not afford to write multiple versions of your code, one for each architecture. You really needed to, you know, the size of our application development teams is not going to increase. You have to port to these new architectures. Maybe that's possible for most applications, but to port to every vendor's offerings is just way beyond what an application development team can do. So you really want to have portability. That's the #1 issue. But we also need good performance. You know, when you do that, do you need to have perfect performance? Not really. You just have to have good enough performance with a single source code. So you may not get the absolute best performance that you could get on a piece of hardware, but you would rather have code that can run everywhere. So this is the performance portability. And then we can't ignore productivity. And there's 2 aspects to that. One is the initial port, and the other is long-term application support. So this is really crucial for most application developers, and this is what limits applications from moving to the GPU or to any of the accelerated architectures that we have today. So let's look at our language paths for the AMD GPUs. And, there's several different levels of languages you can use for your application, and the same answer is not necessarily the best for every application. It depends on your application, the characteristics of your application, and it also depends on your programmers, you know, your developers. What are they comfortable with? And so we'll cover 3 different classes here. One is the native or low-level languages where you're close to the hardware, and that's sort of like, you know, a rock climber. You still have to have a lot of skill for that. And then the next level is this pragma-based languages. It's a little higher level language. You just insert these magic pragmas, and all of a sudden your loops are running on the GPU. So that's attractive for many application developers, and the limit in that area is really the compilers have to develop the capability to support that. And they're pretty good today, but compilers take longer to develop than a library. So we're on that path to where many applications are able to use pragma-based languages. And then we have this higher level performance portability languages. Frameworks, this is in the DOE, this has been Cocos and Raja, but there's others, YACL, which is yet another kernel language, and ACL, and many others that have sprung up that offer this even higher level of performance portability. They typically are implemented using templates so they can bypass the compiler, at least for now, to get it out to every system as quickly as possible. So you have multiple choices depending on your application, and you have to look at what the capabilities are for each of these and what you're comfortable, what kind of programming level you're comfortable working in. So we'll go a little bit more into that. So our native or low-level languages, that is for AMD, that is ROCm. So ROCm is the language that drives our GPUs. For NVIDIA GPUs, it's CUDA. And on top of ROCm, we have this heterogeneous compute interface for portability, which is called HIP for short. And if you program to HIP, you can either run on NVIDIA or AMD. And as I said in the outset, we're committed to portability, and you can see that right here. And why do we have this kind of design in our software? Well, it's quite clear that as an application developer, he's not going to write a separate piece of code for the AMD GPUs, and we're supporting that idea. So we're going to make it look as close as possible to the NVIDIA software at the API level. The underlying software may be quite different to customize it for the particular architecture that is in the AMD GPUs. The earlier language AMD had was OpenCL, and that was a really good design of a portable low-level language. It was more verbose, and it was different enough from CUDA that it never got traction. Vendors would only optimize OpenCL for their particular architecture. So it wasn't as portable, especially from a performance standpoint, as people really wanted it to be. So converting from CUDA to HIP is really straightforward. It's really easy to take a tool that will do the majority of the conversion, because basically the same calls are implemented in the ROCm software layer. So we have a couple different scripts that you can use to do that kind of work, and it's really just replacing the CUDA calls with either a ROCm call or a HIP call. Now, I strongly recommend a HIP call because then you are portable. And you still have to do some optimization effort to tune the performance on the critical loops. Now, you still require a different source on CPU and GPU. It does require some effort. And for large applications, that can still be a significant issue to porting to GPUs. So pragma-based languages, we have OpenMP. That's what our primary support for the programming AMD GPUs is OpenMP. And it's implemented using LLVM. We've been working with LLVM for longer than I believe any other vendor. And most of the compilers are now moving over to LLVM. So the Intel has moved over to LLVM. NVIDIA compilers moved over to LLVM. Cray, their C and C++ are moving over to LLVM. Now, LLVM is a compiler infrastructure, so they still put some of their secret sauce on top of the LLVM software, but it's become very difficult for a compiler writer, a vendor to completely implement all the features in a language today, and so we have a general movement of everybody over to LLVM, and LLVM primarily supports OpenMP. OpenACC was the earliest pragma-based language, and originally it was released by 3 vendors that were not willing to wait for OpenMP to come out with their standard. So there were 3 companies that came out with that. That was PGI at the time, Cray, and one smaller company. Right now, that smaller company went out of business. Cray is shifting over to OpenMP and their C and C++ compilers. And so really NVIDIA is the only vendor left that is strongly supporting OpenACC. And they're even implementing OpenMP as well. So we see a shift over to OpenMP throughout the HPC community. And one of the things that many of us have been tracking and have been interested in is, if these pragmas work, could we just integrate that into the standard languages? So this has been discussed for 30 years, that we could just have a different keyword on a loop specifying that you could do this in parallel, for each, do concurrent, etc. And AMD has just released a version of their compiler that supports parallel C++ that meets the standard, the C++ standard, and does GPU offloading by specifying execution policies. That's also in the Fortran standard, but has not been implemented yet by AMD. It's still early days on this thing, getting this implemented with a standard language implementation. The compilers still have a lot of work to do, but it is possible to use just standard language to write your program. So we see things getting easier with time to port to GPU, to running on GPUs. Okay, so our higher level performance portability frameworks and the leading implementations for that have been Cocos and Raja. Cocos out of Sandia National Lab, and Raja out of Lawrence Livermore. There's a lot of similarities between those 2 languages and the other kernel-based languages. And basically what they're doing is using templating and lambda-based constructs to send the compute part of the operation to the GPUs. Both of these support AMD GPUs, and they were developed at these laboratories so to make it easier for the many application codes they have to port to these new architectures. And for example, when Aurora comes online, Cocos adds that capability, and the application doesn't have to do any work to run on Aurora. So tremendous advantage for large code bases, single source that runs on CPU, GPU. But this really only works for C++ codes right now. And so if you're a C++ code, this might be attractive. they do a lot of the work for you, and they really pay attention to performance. So they will often get as good a performance as you could get with a lower level language. So you can see we have a rich set of languages today. There are other languages. Most of these will run on AMD GPUs to some level. There may be gaps in the implementations, but in general, they do run on the AMD system. So SYCL, Adaptive CPP is the current SYCL library that will, or compiler that will run SYCL code on AMD GPUs. Julia, we've had applications run on AMD GPUs written in Julia. Python, many of the Python libraries also run on AMD GPUs, even though they're sometimes still called things like CuPy. They have been modified to support AMD GPUs as well. The machine learning AI languages, most of these run on AMD GPUs, and some of them, the language developers are using AMD GPUs in their development process. Okay, so I'm going to pause here, and Giacomo's going to take over, but do we have any questions? I see Giacomo's been answering some of these. Let's see if there's any I should address. So there are still NUMA-like effects with memory. So memory depends on how the system is configured, how many NUMA regions are configured in the system at boot time. But there is, in general, you have memory that is closer to some parts of the CPU and some parts of the GPU. And if you're on the right CPU, you are closer to a particular GPU, which will reduce your memory transfer costs across the bus. So affinity, process placement can be important to improve performance on these devices. That's a deep topic, and Giacomo has added a link that goes into that in more detail. We have a whole talk on that, and it's a complicated topic. Do you have to worry about that right away? Well, no, but when you start getting to really eking out the last bit of performance, that can become critical. It also helps reduce the variability in performance from run to run. And then with the MI300, it's very similar with NUMA regions to that MI200 article. The details are a little bit different, and so the article talks about the tools to query your system and get a graphic out that shows where everything's placed, or text output that tells you which GPU is closest to which CPUs. So it takes a little bit of work to see what your particular architecture is. But even within the MI200 series, we have variation from site to site with how the devices are laid out. And on some of the systems like Frontier and Lumi, they will actually reserve one of the cores for the operating system. So you have to look at what they're doing at the local sites to reduce the variability in the runs from run to run. So that takes a little bit of effort to get good process placement and affinity. How important is that? Well, if you're bandwidth limited, you really want to get all your memory channels engaged and get your CPUs close to the GPUs. So it can be important. Do we have any other questions? And you're free to raise your hand or speak, unmute and ask the question live. Okay. Well, I hope that gives you a good overview of the architecture. I'm going to hand it over to Giacomo, and he's going to go into this HIP and ROCm languages, the lower level languages for AMD GPUs.
Thank you, Bob, and thanks everybody for being here. Yeah, so Bob has already mentioned something about HIP, and in this part of the talk, we're gonna talk a little bit in more detail about what HIP can do for you and how you can leverage it to program your GPU accelerators. And one of the main features of HIP, as it's already been said, is that it allows for great portability because you can just program in HIP, and even if you have NVIDIA devices, then your code will just work also on NVIDIA accelerators. And as you may already be aware, it's all about the host and device in this game that we got involved in. And by the way, there's this bit of terminology that we have to keep track of, which is that the host refers to the CPU and the device to the GPU. So basically, the CPU is called the host because that's where you are calling your API functions to then do work on the GPU. So in a way, it's hosting the device, and it's based on a C++ type of syntax, whereas the device, it's more like a C type of syntax. And for host code, there's only one entry point, which is the main function, whereas the device code has many entry points, which are the kernels. So in the next slide, I'm showing you a very high-level overview of some of the API calls that will be relevant to you with HIP. And obviously, if you go ahead and check the documentation linked at the top of the slide, you can see a full list. But here are the main ones for starters. And as you can see, we have some calls to query our device and identify and get specific GPU devices that we may want to work on. Then we have a set of memory management calls that will allow you to allocate and or copy memory. We have calls that let you deal with the concept of streams that we will touch on briefly during this presentation, as well as events that basically let you synchronize between different streams, though we're not going to have time to go deep into those here. Oh, let me just mention that originally in HIP, there was this API called HIP launch kernel GGL, which was what you would use to actually launch a kernel. But now we're also supporting the triple chevron as CUDA. So if you're already familiar with CUDA, then you will see several similarities also with HIP. And then we have information on how to query your threads, and we're going to talk about that in just a second. Yeah, so basically, in case you're already familiar with GPU running, you may have heard already of the concept of a thread grid. So basically, when you execute code on a GPU, the threads are the single unit that performs the computation. But these threads, which are software objects, can be seen as being located or composing a grid, much like a mesh, if you want to see that from an application person point of view. And it's important to remember that we have to differentiate between software objects and hardware objects, and the threads in this case will be software objects. And before executing your GPU kernel, you have to define this grid of threads. And you're gonna pass that information to your kernel, and then the kernel is gonna execute on this grid, which doesn't really exist in the hardware, and it's more of a construct. So basically, this grid is composed of equally sized blocks of threads that in AMD terminology are called work groups. And each block is made up of several threads. And something to be aware of is that the terminology between AMD and NVIDIA is not exactly the same, also for some technical details. And in fact, if you are familiar with the concept of warp from NVIDIA, which is basically a chunk of 32 threads, the equivalent for AMD is called wavefront, and it's composed of 64 threads instead. And the thread block for AMD is called workgroup. So just to visualize this briefly, in this slide here, there's a one-dimensional grid, but you could have 2D or 3D grids as well. And here you can see that the blocks are marked with different colors, blue or orange. And in this particular picture, each block is composed of just 4 threads. So the useful thing, and this is going to be important for your performance, is that you can actually query information from this grid. So for instance, the .x just means that you are interested in the, let's call it X direction of your grid. And so you can basically compute the global index of one of your threads in the grid, and this is this ID that we have here, by getting information from the local indexing. So for instance here, this block dim X is telling you how many threads each block in the X dimension of the grid has. And in this case, it's just like 4, because we have only 1D grid, and each block is composed of 4 threads. This block ID X is basically telling you the local indexing of the block in the grid. So block ID X2 means this the third block here, the second blue one. And then thread ID X is telling you the local indexing of your thread within the block, basically. So that means that once you put that all together, we are looking at the thread that has global index of 11. So you can get the global index of your thread within your grid by using the local indexing. Much like a matrix, if you want to see that in that way. And obviously, as I said, you can have 2D or 3D grids as well, but that's the most you can have. So if your problem has a higher dimensionality, then you're going to have to map it to a 3D grid, for instance. So this is just a quick example of some of the features that you may see when you're using HIP. So first of all, you're going to have to include the header for the heap runtime here. And then you're going to have the definition of your GPU kernel. And something to notice here right away is, first of all, that GPU kernels have to be declared as void, so they're not going to have any return value. And also, if you're not familiar with GPU programming, you have to keep in mind that when you are writing the kernel, you have to think that each thread in your grid is going to execute the same operation at the same time. So basically, there are two things to make sure of. One is that you have enough threads to cover the number of operations that you want to do. And second, you have to make sure that there are no race conditions for which a thread could try to access information that's not up to date, or even try to override something that another thread has written. And obviously there are other things to be mindful about, but these are the two things from which you should start, I think. So in this case, we are just multiplying all entries of an array by 2. So we are not worried about race conditions. But we do have to be careful, because you see here we have this if statement that basically makes sure that we are not going over the size of this array. Then the next thing is to just allocate some memory on host for what concerns the array. And then we are allocating memory on device with heap malloc, and then copying the memory from host to device so that we can work on the device array in the kernel. And as we've seen already with Bob's presentation, there are situations where you may not have to make these copies explicitly if you are relying on page migration or if you have an APU. But sometimes making explicit memory management will help your performance. Here, the important thing to notice is that we are defining the number of threads per block as a multiple of 64, and then we're also defining the blocks on the grid. So basically, threads per blocks and blocks on the grid are the two types of information that you need to have before you actually run your kernel. And it's important to do that in a somewhat crafty way so that you can have a good performance. Obviously, like you can start doing it in a somewhat naive way to just have your kernel run, but then to actually have optimized performance, it makes sense to spend some time thinking about what's the best way to define the grid. And then after the computation on device, the information, the data is just copied back to host so that you can access it. So there's a reason why this idea of a grid exists, and it's because it somewhat maps naturally to how the actual hardware looks. And in fact, here I'm reporting the schematics of a compute unit for an MI200 series accelerator. And in general, we have that threads within a thread block or work group execute on the same compute unit in chunks of 64 threads that we call wavefronts or waves. And these threads can share LDS memory and L1 cache and can also synchronize. And this is very important to be aware of, because LDS memory is very fast to access, and therefore you can leverage this feature of the software and how it maps to the hardware to optimize your kernels. For instance, you could do a matrix multiplication that uses tiles, where each tile is allocated as shared memory among threads, so that all the threads operating on the same tile share the same information. And so that computation would be very fast. So this is just to mention an example of how you can leverage this to make your kernels run faster. And in general, it's also good to have good occupancy, meaning that you should try and use most of the resources of your GPU, because if the wavefront stalls, then the compute unit is very quick at context switching. And so basically you can hide latency and keep going fast. And it's good practice to also make the block size a multiple of 64 because of the wavefront size. And yeah, something quickly to mention also is that heap calls can be blocking or non-blocking. Blocking means that the host is not doing anything until the call has reported complete. So basically, mem copies are blocking, whereas kernel launches are non-blocking. So the host can launch the kernel and then just proceed to doing something else as the kernel keeps working. And you can make asynchronous copies, but to do that, memory needs to be allocated as pinned or non-pageable on the host using heap host malloc. And then you can proceed with heap memcopy async. So here, something to be aware of is this bold word stream, which is the concept that allows you to actually proceed with asynchronous instructions. So basically, a stream is just a queue of tasks in heap that could be kernel launches, memory copies, or events in general. And tasks in a stream are enqueued in the order they're received. So if in your code you have kernel launch 1 and kernel launch 2, then in the stream, you're going to have kernel 1 first and kernel 2 second. And these are the API calls that allow you to create or destroy the streams. So basically, there's the idea of this null stream that is a special stream that you can define either by passing 0 or null to your kernel. And any task in the null stream will not begin until all previously enqueued tasks will have completed. So you can already guess that blocking calls will exist on the null stream. And for instance, here, just a visual example of what happens if you just put everything on the null stream. So here in the kernel, the last argument will be the stream ID. And here you're just calling, you're just launching 4 kernels sequentially, let's say, all of them on the null stream, and so they will just execute in order. But you can leverage this idea to actually make them execute asynchronously by creating 4 different streams and then providing each of those to the kernels, so that now you see that nothing's executing on the null stream and kernel 1 is on stream 1, kernel 2 on stream 2, and so on. So here, for simplicity, all the kernels look like they have the same duration, but that would not be the case in general. And so basically, you can leverage that idea of streams, and also the fact that AMD GPUs have separate engines for copies and compute kernels to overlap memory copies and execution. So in this case, you would have 3 copies, 3 executions, and then 3 copies again that you could do on 3 different streams, so stream 1, 2, and 3, and you'll see that basically my kernel 1 is executing at the same time as on stream 2 copy host to device is happening. So this is something that you can use to make your computations faster, this asynchronous overlap of events. And we also have calls to synchronize to make sure that basically at the synchronization point, there's the necessary exchange of information, so that you are sure that after that sync point, all the data is current. And we have, for instance, heap device synchronize, which is a heavy-duty sync point, which basically blocks the host until all work in all device streams is completed. So this is very effective, but you also have to be mindful about how much you use, how much use you make of that. And you can also synchronize streams with each other, but we don't have time, unfortunately, to talk about that. But there's details in the documentation reported here. And let me just say something brief about ROCm as well. So as we said, ROCm is the language that you would use on AMD GPUs to actually access the hardware. And ROCm has a lot of libraries that are optimized for scientific computing. So for instance, if you're in need of using BLAS, we have heap BLAS, that's an umbrella that would invoke QBLAS if you're running on CUDA, on NVIDIA hardware, or ROCblast if you're running on AMD. And if you know that you are gonna be running on different GPUs, on different vendors, then it's better to use HeatBlast. But if you already know that you're going to be running only on AMD, then for performance, it's better to just use ROCblast directly. ROC calls, I mean. So yeah, so we have many options for libraries, like ROCblast would be a drop-in replacement for QBlast. We have fast Fourier transforms with ROCFFT, ROCtrust, and then others as well. ROCsparse, ROCsolvers for linear solvers and sparse matrix multiplications. And you can find a complete list at this address here at the bottom. So yeah, one last thing is that ROCm allows you to query the system and get important information on the power, for instance, or the temperature, or the use that you're doing of your GPU. And if you have installed ROCm on the usual location, so opt/ROCm, then you can just run ROCm SMI and get all the information. Though to change the frequency and power limits, you're gonna need pseudo privileges, because you know the privilege of melting your system is not for everybody. At least you need to be in the suitors group. So yeah, so with this, I'm just gonna give it back to Bob, and thank you for your attention.
Okay, we're going to launch right into OpenMP on AMD GPUs. I'll be going a little bit faster because we're short on time, but also I'm just going to compare to what it looks like for the lower level languages. So to compile OpenMP on AMD hardware, you have to add a few flags to your compile line, your build system. You do need to add what compute architecture you're running on, and here's a list of the architectures that we're most concerned with today. And you know, the idea still is this host and device model. So it's embedded in the OpenMP pragma structure as well. And device generally means GPU, and it could be the device really could be anything, at least in concept, including an FPGA or even another CPU. And to move memory back and forth, you're going to use these map clauses. Target means it's going to offload to the GPU. Map is going to move the memory from the host to the device and back. And so these clauses, in this case, we're looking at Fortran style directives. They're very similar for C and C++ pragmas. And here is an example of a Saxby loop where we're telling the system that we want this loop to be run in parallel. If you look at it closely, this is parallel on the CPU, so we don't see the target clause on here, so this is running in parallel on the CPU. And you know, we can also use the BLAS library for a loop like this as well. So this is the next slide. We're going to see how we make this run on the GPU. So these device constructs in C, it's going to be a Pragma OMP target. In Fortran, OMP target. Target is basically saying to run it on the device, and generally on the GPU. There's many clauses you can add to these pragmas. We're not going to go into great detail on those. We're just going to hit the more common ones. But you can see how this basically, the compiler is doing that transformation to the kernel language for you. So you do less work in porting to the GPU. So the compilers are actually pretty good if you're all within one execution unit. They know the sizes of things. When you say map, it can tell whether it's on the device or on the host. And in this case, when we say Pragma OMP target, it knows that it has to move the memory over to the device. So the compiler in this case, because it's all within a single execution unit and even within a single function, it knows the sizes of things. But in general, it may not know the sizes, it may not know when to move things, and so it is good practice to always put this map clause in there and tell it to move that memory over, and what memory needs to be moved over, and what memory needs to be moved back. And this is a lot of the initial optimization, not, you know, don't move memory if it doesn't need to be moved. And that will greatly speed up your code because the movement of memory over the PCIe bus is slow in comparison to many other parts of the execution. So when you have a subroutine where the variables are passed in, you have to help the compiler by telling it how much memory to move. And this can vary from compiler to compiler, so it's a good practice to do that in any case, even when on your particular compiler it is able to detect the size of things. It also varies a lot between C and Fortran. Fortran, it can often detect the sizes a lot better than within C. So target, whenever you see that target construct, that means it's being moved to the device. And it's synchronous, so it will block on the end of the loop. And then you have a lot of additional clauses you can add to tell it to run in parallel on the GPU. You could run serial. In some cases, you want to do that. But in general, you're going to want to run in parallel on the GPU and take advantage of the size of the GPU. And in fact, on the GPU, you have thousands of compute units to try to keep busy. So it takes a lot of work to keep them busy. So here we now have OMP target map, and then we tell it that on this loop, we want to run it in parallel. So parallel for SIMD. Parallel for is telling it we want to run in parallel. SIMD tells it we want to vectorize on the CPU, and on the GPU we're going to, it tells it we want to engage all the threads. Now SIMD is not necessary on the AMD GPUs, and on many of the GPUs they don't implement the SIMD. The parallel 4 is enough, but there's still a few implementations where SIMD is important to get the full parallelism. Okay, so teams, this is going to engage more GPU compute units. And once you get your kernels running in parallel, really we focus mostly on the data transfers. We want to minimize the data transfers. In some applications, you want to move the data over to the GPU or even create it on the GPU and just keep it there, because moving back and forth is an expensive operation. Sometimes you can overlap the compute, the data transfer with some of the computation, but in general, it's good practice to be minimizing that data transfer. Some applications need so much memory, they have to do this offload model where they move a block of data out to the GPU to operate on it. So it's a little bit dependent on the type of application you have. But you can see from the relative speeds of memory and the PCI bandwidth, at least today, that you still want to optimize or minimize the amount of data transfer. Now, with each generation of PCIe, they're basically doubling the bandwidth, so it's getting less cost, but it's still going to seem expensive in comparison to the other operations. So OpenMP compilers can do a lot of the work, you know, the work at converting code to run on the GPU. You have support for C, C++, Fortran, so you have multi-language support. You can have part of your application in Fortran, part in C. It's fairly mature. Now, compilers are still implementing some of the more recent features in the standard, and there's a little bit of variation across compilers. But it is all moving towards a consistent implementation across vendors, across compilers, and it really is a good choice for many, many applications. It gives you good composability, so you can mix what languages you're using, other GPU programming languages. Though we don't talk about it here, you can mix OpenMP code with HIP code. In fact, we often recommend that you program in OpenMP for most of your code and only drop to HIP or HIP libraries for the performance critical parts of your code. Okay, so performance portability languages. There's a couple different languages here. I'm going to actually skip this so that we have a little bit of time for Giacomo to go into the tools. So I'm going to go ahead and skip, but you can look through this these slides on Raja and Cocos. So they basically offload to the device for you, so much in the way the Pragma-based languages, they do a lot of the work for you. It looks like standard C++. Support has been in the Cocos software for quite a time now, and it's now at production status. There's two basic requirements for a GPU language. One is execution capability and the other is memory handling. We've talked a little bit about this, but you can sort of, if you see the pattern of the memory movement and how to specify running on a loop in parallel. They're really fairly similar across languages. I'm not going to go into the details on those abstractions in Cocos. And we'll go right to the AMD tools. Take it away, Giacomo.
Thank you, Bob. Yeah, and we're gonna keep going with this for a little bit. And if anyone has to step away, don't worry, the recording will be on the event page in a day or two, so you can come back and pick it up. Okay, yeah, so we have quite a rich set of tools at AMD that are meant for different scopes. And for instance, this bit of presentation has been set up so that it flows in a way from a certain example code that's thought of being written in CUDA, and then that would be transferred to HIP and then debugged and optimized with our tools. So we have, as Bob already said briefly, we have HIPify tools that allow you to basically port your code from CUDA to HIP. We have debugging tools with ROCgdb that comes directly with ROCm, as well as ROCprof that would be the provider. But we also have newer tools that come off of AMD research with our Omnitrace and OmniPerf that I'm going to show you what they can do for you and how they can be useful. So as I said, we are going to be focusing on this example that you can clone from our GitHub repo on HPC training examples here. And this is based off of Bob's book on HPC and GPU computing. And this is a simple example that is meant to symbolize something that you could find easily on real world application codes. And it's basically just a 2D mesh that's partitioned among MPI ranks, and the solution is initially defined on a cell-wise basis, and then there's a kernel that's averaging the solution with a 5-point stencil. And we have halos to enforce boundary conditions, as well as parallel exchange of information when a parallel run is performed. And this halo exchange, where the ghost cells are updated, is done first horizontally and then vertically, as in the picture. So as I said, if you clone our repo, you will find a version of that code that uses CUDA calls that you can modify to become HIP calls with several different tools. For instance, we have HIPify Perl. That's the easiest one for a quick scan of projects that basically performs a string replacement for which CUDA basically becomes HIP. And as you can imagine, this is not the most accurate that you can have, but it's a good way to have a quick scan of your project. Something more elaborate is HIPify Clang that also is going to give you some error messages and warnings, and it's more robust. But to use it, you're going to need the Clang compiler, and so you also need to specify those includes that you would specify when you actually use Clang. Something to be aware of when you're going through the process of HIPifying is that HIPify tools don't actually check the correctness of what you have HIPified. And also you have to be on the lookout for hard-coded warp sizes of 32, because as we said, wavefronts for AMD have a 64 thread size. And also HIPify Clang, for instance, modifies code in place. So it's better to make a copy of your code before you actually run it with HIPify Clang. On the plus side, though, HIPify Perl and HIPify Clang can both convert library calls. So QBLAST will become HIPBLAST, for instance. And if you're interested in more detail, you can take a look at this portability blog post that has more information on this topic. Something else that's available is this HippieFly tool, which basically is a header that intercepts the CUDA API calls and swaps them on the fly with HIP calls. So basically that would allow you to not at all change your code. You can just include this header. However, the catch is that you need to use, your code needs to have CUDA API calls that have an exact match on the HIP side. So performance has to be evaluated on a case-by-case basis. But this tool is also out there and can be useful. So for what concerns how to actually run, for instance, HippieFly Perl is just very simple. It comes with ROCm. So if you load ROCm, you have HippieFly Perl, and you can just pipe the output of the hippification to a new file. And you can try this yourself by cloning the repo, as I said before. So for what concerns debugging, as I mentioned, we have ROCGDB that comes with ROCm, and it's based on the GNU debugger GDB. As you'll see, some of the commands are straight out of GDB. And in this set of slides, I am going to use ROCGDB to track down a bug in a version of that Ghost Exchange code that I showed before. So basically, the bug here is not a runtime or a compile time bug. It's just a bug where the solution is not what it should be, which in my opinion is the trickiest bug. So if you want to try it yourself again, you just need to clone the repo and then cd into this folder, which is the one that has the bug. So basically, in this example, the mesh is partitioned among 4 MPI ranks with vertical stripes. So the numbers that you see in the blue boxes are the values of the solution for the cells owned by each MPI rank. And what's outside is the halo. So for the one on the top left, the column on the left is the boundary, and the column on the right is partially the boundary at the top and bottom, and to the right is the information sent from the process on the right. So at the top, this is how it should look like, and at the bottom is how it instead looks. So basically, you see that, for instance, the values of the solution in the red box are not what they should be. However, you see that to the right of it, we have 2.6, and that's the value of this solution owned by the next process. So this tells you that the error is not an MPI error, it's just an initialization error. So your process is doing something wrong at init time. So to track it down, we're gonna use ROCGDB and place several breakpoints just by basically running ROCGDB with the GUI, with this -TUI, and then the command B and then the line number is gonna set a breakpoint at that specific line. So if you try it out, line 188 and 197 are lines where the init kernels are called, because we've seen that the problem is where the initialization happens. And you can visualize where you located the breakpoints within ROCGDB just by doing IB, and it will show all the breakpoints that you have. The important thing is that when you run that command, IB, it's going to show that each breakpoint has a num associated, which is kind of like an ID. So when you want to delete a breakpoint, you're just not going to do D and the line number at which the breakpoint is, but you're going to be doing D and then num, which is the ID of the breakpoint. To run the debugger, you can just do R. To step to the next line is just N as in next, and then C to continue. So the very good thing about ROCgdb is that with P, it lets you print the values of arrays that could even be on device. So that's really good because you can access, you can see device arrays from the host with ROCgdb just by doing P and then the array. So if you follow what's in this slide, you can find out where that entry that's not correct in the output is switched to an incorrect value. And you see that happens right after the call of this init core 2 GPU kernel. So we can go ahead and insert the breakpoint inside the kernel, and that will allow us with this idispatch command to actually show the thread grid that's used by that kernel. And I think that's a really cool tool of this debugger that actually shows you your grid, basically, your thread grid. So here we see that the problem is that in the y direction of the grid, so we have allocated a two-dimensional grid, and in the y direction, the block only has 2 threads, whereas we've seen that each process owns 4 cells of the mesh. And therefore, the problem is that since each block in the y direction only has 2 cells, the initialization, sorry, not 2 cells, only has 2 threads, the initialization can only touch 2 of the 4 cells that you have on your process. And therefore, to fix this bug, we basically have to make the block size larger. So this is an example of how we can use the debugger to actually dig deeper into the GPU features of our code and uncover what the problem is. Something else that we have are profiling tools, and for that we have ROCprof, which comes directly with ROCm, just as ROCgdb, and it can be used to provide traces of GPU kernels or heap and HSA API and copies, and those are saved as JSON files that you can visualize in Perfetto, which is a tool that exists on your Chrome browser. So if you type this address on your Chrome browser, then you're gonna open up Perfetto, from which you can load these JSON files and visualize the traces. And one cool thing about ROCprof is that it lets you obtain information from each kernel about how long it takes for them to run, and also the percentage that each kernel takes up of your computation. So you see that running that command on our Ghost Exchange example, we can see that the blur kernel, which is the one that actually modifies the solution by averaging it, is the one that takes up the most of our computation. So this information here is very important for anyone that's interested in optimization, because obviously the kernels that take up the most time are targets for optimization. So here in this case, we have the one that actually advances the solution and the one that initializes it. One of the two that initializes it. Yes, so ROCprof can show different types of activities, as I said, heap or HSA, and these are the flags that you have to include to show that activity. And on Perfetto, that activity will look something like this. So this is a screenshot of what you would see on Perfetto, and you can see that the traces appear as basically colored rectangles. And here you can see heap API calls, such as heap device synchronize, and also kernel calls, such as the kernel to advance the solution, the blur one, and the one to enforce boundary conditions. And you see here this bar at the top gives you immediately information on the duration of the kernel. And to obtain that, you just have to click on the specific rectangle and then type the M key on your keyboard. Or you can just double click on the rectangle and it will show you detailed information like this on a different tab that pops up from the bottom, such as the duration over here and the name and the stream ID and other useful information. Yeah, so ROCprof can offer several other features. Most notable is the option to annotate your code with ROCtx. So basically, if you use ROCtx to annotate your code, when you go ahead and look at the traces on Perfetto, you will see user-defined traces to help you kind of have a better idea of what's happening in your code. This is like the evolved version of print statements. Let's just put it that way. And we also have holistic tools such as Omnitrace that are available to you. And Omnitrace is the go-to tool to actually track MPI activity that's not tracked with just ROCprof. This comes out of AMD research, so it's not in the ROCm stack and needs to be installed accordingly, separately. Though Bob and I have worked on several installation scripts that are available on GitHub here in our modern installation repository. So for instance, you can just take the Omnitrace shell script from here and install it in your system. So that's a tool that we also have available. And with Omnitrace, you can instrument your binary and then basically run Omnitrace directly on your instrumented binary. And then you can decide what type of information you want to see on your traces, which are also visualized in Perfetto, but they're not JSON files, they're proto files. And you can decide what to visualize in this omnitrace.config file. And this little graphic here is the one that you should see when you're running Omnitrace, and it tells you what's the version, what's the compiler, and so on. So if you see this, you know that Omnitrace is running. And this is, again, how traces would look produced by Omnitrace. This is a proto file. And if you're running with MPI, you're going to have a proto file for each MPI rank. And you see here that you can actually visualize MPI activities such as MPI receive, for instance, that you couldn't see with just ROCprof. So this is how a snippet of the Omnitrace config file looks like. And you can see that you can turn on or off HSA activity. You can decide how many CPUs or GPUs are sampled. If you see too many CPUs, you can just put a 0 here and it's gonna simplify the look of your trace. And also this is gonna print a TXT file called wall clock, which basically shows you the host side timing of each of your calls. And there's a very recent presentation on Omnitrace that goes in a lot of detail that we recommend you check out, and it's been done for Oak Ridge National Lab, and it's linked over here. So the last thing I want to touch on is OmniPerf, which is also from AMD research, so it needs to be installed separately. And we have a script for that too on the modern installation repo. But OmniPerf is great if you are interested in optimizing a specific kernel. And for that, there are several ways to diagnose. For instance, we have roof lines that can be displayed for you. And a roof line, if you're not familiar, is just this little diagram that has the arithmetic intensity at the bottom on the x-axis and the attainable flops on the y-axis. And you see that this line here is the bandwidth bound limit, and the green one is the compute bound. So basically, you cannot have any data point to the left of the bandwidth bound or compute bound lines, just because that's not possible from a hardware point of view. And you would like your data points for your kernels to be close to the compute bound limit. So you can see a roof line for your specific kernels. And here I have a roof line for the blur kernel, which was the one averaging the solution, and also the one that was taking up the most time in our computation before. We've seen that with ROCprof. And we see that the blur kernel is very close to the bandwidth limit, whereas the init core 2 is very far from it, which means that there's a lot of room for improvement to bring it kind of like up and to the right. And something else, and I'm gonna finish with this, is that with ROCprof, you can do something very cool, which is you can test improvements that you've done specifically on your kernels, because you can generate profiling data on your code, and then you can modify something on your code, like say a specific kernel. For instance, here I modified the grid size, and then I ran it again with this v2 name. And then you can run OmniPerf analyze, and that's gonna compare the performance of the two different implementations and show you how they fare, how they compare head to head on several different counters that you may be interested in, or different metrics, like for instance the grid size, workgroup size, and total wavefronts. And again, unfortunately, we don't have a lot of time to go into detail, but there's a presentation that's been done on OmniPerf in April that's very, very detailed, and it's gonna give you all the information that you need, hopefully. So yeah, so with this, we are concluding our presentation, and thank you so much to everyone that stuck around over time. We really appreciate your presence here and your interest. And then I'm gonna turn it back to Bob and Claire.
Well, thank you, Giacomo. And we did run a little long on this. It's hard to compress everything into a short period of time, but I hope you've gotten the impression there is a rich set of tools. There's a rich array of languages and support for programming GPUs today. And I hope this encourages you to try out GPUs and try out AMD GPUs in particular. So we'll conclude with that. If you have questions, go ahead and put them in the chat, and we'll continue to answer them.
Well, thank you both very much indeed. Yes, sorry to the audience that we overran, but I really think that was a very valuable overrun because you covered so much and so very clearly. And I hope everybody else enjoyed listening to that as much as I did.
Yeah, and we will have more detailed presentations in the fall on each one of these topics. We could go a lot longer. So thank you, and we hope to see you in the future.
So we'll wrap up now. Thank you very much to Bob and to Giacomo. Thank you to everyone who attended, and especially those of you who stayed to the end. And the recording will be added to the event page. It'll probably take me a day or two just to do the editing, and then that'll be available for anyone who wants to review or catch up. Thanks very much, everyone.
Thank you very much, Claire.
Bye-bye.
Thanks, everyone, for attending. Bye-bye.